All right, everybody. So today you're going to be working on finishing up the problems that were at the end of the in-class worksheet from a couple days ago. And we did 68 in class yesterday, Wednesday, and started number 69. And so solutions, by the way, from all these numbers 69 through 71 can be found on the Moodle site. But I thought I'd give you some pointers for number 70 um, today, because I think that that might be something that might be a little bit of a struggle without any pointers. So just a reminder though that today in class you should be working on these three, numbers 69 through 71, and section 12.7 may be helpful when doing this. So with number 70, you're looking at a pulley situation. So again, we're constrained with ropes and pulleys here, the movement of this whole device. And so we have a more massive box that I'm calling box 2 over here and box 1 over here to the right, and then we have the pulley. Box 2 is a mass of 4 kilograms, box 1 a mass of 2 kilograms, and so when this is released, it's going to move in this sort of a fashion, in this counterclockwise fashion, so this pulley will have a positive angular acceleration. So I drew a free body diagram for box 2, for the pulley, and for box 1. And so you can see here the tension up, the weight or the force of gravity down for box 2. For the pulley, you have the axle holding it up. I'm calling that a normal force. You have the force of gravity, or mg, down on the pulley. Those two cancel each other out, and they do not contribute any torque. And then for box 1 over here to the right, you have tension 1 going up and the force of gravity going down. So what gets a little trickier with this is, well, first of all, I just went to each individual item and set out Newton's second law. So for instance, for box 2, we have tension 2 in the upward direction. We have force of gravity in the downward direction is going to equal mass 2 times acceleration 2. And I should put this in here as well, a subscript 2 to be very specific. And for the pulley, we only have, I'm doing this now, net torque equals the I times alpha, I being the moment of inertia. And so we have in the positive direction T2 times the radius r of that pulley. In the negative direction, so subtract tension 1 times the radius r. And really we have the sine of 90 degrees in there on both of these as well, since these forces are occurring at right angles. And then the problem also described that there is friction within this thing as well that's going to act against the direction of motion, and it provides 0.5 Newton meters worth of torque. And since it's going to be acting in the direction, well, when this thing is released, this box 2 is going to fall, box 1 is going to go up, and so the resistive motion is going to act in the direction opposite to the motion, and so it's going to be a negative torque on here as well. So you have to include that torque due to the friction in this problem as well, and then set that equal to the moment of inertia times the angular. Continuing on, looking at the constraints that we're dealing with. So in this particular case, if item 1 here, box 1, if that has a positive acceleration, then item 2 over here is going to have a negative acceleration. Since they're constrained, they are hooked up to each other, they are tied to each other, so as one accelerates, so is the other. But this is what the directions are going to be. They're going to be in different directions here, and so that's why I have the negative sign here and the positive there. And so that's going to be the acceleration of this overall device. And then also, like we've been talking about, the alpha here is going to be equal to this acceleration times, or excuse me, divided by the radius as well. And one thing I forgot to mention a little bit earlier, this is different than the Atwood's machines we used to work with. The tension here, tension 2, is not going to be the same as the tension 1 over here. That's only in the case where the pulley is massless and frictionless, And in our case, we have friction and we have mass. And so T2 does not equal T1 here. So just keep that in mind as well. So hopefully with these hints, you'll be able to work through number 70. Take these constraints and continue working. Also, you can check out the solutions online and then ask further questions on Monday when I get back. And again, I have number 71 is a similar sort of problem, so see what you can do with that. And again, get as far as you can on it, and on Monday we'll go over questions you have on either of those. Make sure to bring your books again tomorrow. You're going to need that for looking at items that are in what are called static equilibrium tomorrow. So hope you have a good Thursday, and there'll be an update again tomorrow, and then I'll see you again on Monday.